So as I mentioned, 3 presenters today, my colleagues Anthony and Stephen, who have just spoken. So Anthony works for Meyer and specializes in EMAG. Stephen works for Siemens and specializes in this whole area of electric vehicle design and motor design. And myself on the end there, I also work for Meyer and lead the technical team on the pre-sale side. So moving on, just an introduction to Meyer. As you can see from the slide, we get involved in quite a few areas. We have a heavy focus on simulation, but you can generally say we kind of help people through a digital transformation journey in this space. And we're partnering with Siemens. We were recognized as a top partner in North America in 2021. And as well as focusing in on the simulation technology, we do a lot of consulting. We also integrate systems for people in the PLM space, etc. And we have a division which develops software, and we've developed a lot of the software modules which are part of the Siemens Simcenter portfolio, which is what we'll be talking about on this webinar. As again, you can see from the slide, we're a lot of technical people, engineers, all from different areas of industry. We touch on pretty much most industries. We have people in the team who can help in those areas. So yeah, we can help you with simulation, manufacturing, optimizing some of your operations. And we're in a nice position where we can combine those engineering skills, software development skills, and even things in space like AI, where we can take some of your ideas and turn them into reality. So jumping into today's topic. So first we're going to look at a kind of overview of the electric vehicle design challenges, and then we'll sort of drop down a level, if you like, and look at the motor design process specifically. And then Anthony, my colleague, will take you through how you might approach this and the tools and the systems that we can provide to help you do this very efficiently and quickly, reducing reliance on physical testing, etc. So I'm going to hand the ball over to Stephen, who's just going to take us through some of the higher level challenges around designing these kind of products. So Stephen, passing the ball to you.
Thank you, Adam. I hope you can all hear me very well. So yeah, I'm not going to go with like high level challenges and trends of the automotive industry, just focusing really on electric vehicles and what that really means in terms of the new engineering challenges, if you want. And the first one that I think is a really important one is comparing a electric vehicle or a hybrid vehicle, for that matter, to a traditional combustion engine vehicle. There are a lot of choices to be made, and that's the first challenge. It's so that over, let's say, more than 100 years of development of combustion engine vehicles, people have sort of converged on a few standard architectures, and most of them actually have an engine in the front, driving the front wheels, having a cooling system for the engine, which comprises of an oil circuit and a coolant circuit, and that links to an HVAC system, and it's all sort of like predefined how you're going to build a vehicle. But with electric vehicles, them being, well, they've been around for a very, very long time, but actual, let's say, modern electric vehicles, this convergence has not happened. And we see that with a number of, we look at vehicles in the market, you see that there is many different choices being made. So the first question really to answer in EV development is like, what is the architecture that I'm going to follow? Is it going to be one electric motor, multiple electric motors? How am I going to lay out my cooling systems? Is it going to be one combined cycle system for the battery, the e-drive, and the HVAC system all together, or am I going to separate them out? Those questions are really not answered right now. And that's a big choice and a big challenge. At the same time, people are driving toward many different vehicles in the market in a very short time. I hear messages from Volkswagen putting out saying messages about we're going to launch up to 70 new vehicles before the end of the decade. Toyota saying similar things. Think about how many different variants need to be developed, and that with the same engineering workforce, compared to 20 years ago when a company like Mercedes essentially had 3 different types of vehicles, and that was it. So that's really a big pressure there. And third element that I want to highlight is the system integration. And it sort of relates to the architecture choice, but as electric vehicles evolve, people are much more integrating different systems together into a single one. And if I compare, I just take an example, the Nissan Leaf from 2011 and compare it with the 2017 version of it. The 2011 had 4 different cooling systems for the different components of the driveline, each with their own control system associated with it. Whereas in 2017, they all integrated that into one system with one control system, essentially simplifying the manufacturing side of things. But if you think about it, that's complicating the engineering side, because now all these different teams that were working on these different subsystems need to work more together. And that's making life not so much simpler in reality. The other part that the last part that I want to highlight is what we call balancing of attributes. And if you think about it, 10 years ago, people would go out and buy an electric car because they wanted to have an electric car. And they would contend with certain compromises. Now, when people go out and buy a car, it just happens to be an electric car in certain cases. And the expectation is that they buy a car and they don't want to compromise on anything. They want to have the same comfort, the same noise, the same driving comfort, the same build quality, the same everything. It just happens to be an electric vehicle. And so the idea that, okay, we have to focus really on the driving range, the performance of that electric driveline, because we need to integrate it into a car, that focus needs to also broaden in the sense that we need to think of all the other elements that make a good car a good car. So if we go to the next slide, yeah, it's a bit of a different view or a different aspect of all the challenges that we see, is the fact that, and I'm here quoting from a McKinsey report that was looking at the profitability of electric vehicles in the market, and essentially coming to the conclusion that most electric vehicles are not as profitable as they need to be in order to be profitable for the company that brings them onto the market. There are relatively few electric vehicle car companies that are really making good money. And that's just, I think, a fact of this all being relatively new. And you can think of a lot of stuff that could be done in manufacturing and so on, and in product strategy and so on, in order to improve the profitability. But we're looking at development. And when we look at the development, even also there, a number of things that are highlighted are, for example, using a native and modular EV platform. Okay, starting from not starting from a combustion engine vehicle, but just and converting that. No, starting from scratch. A nice example: if I take a Volkswagen Golf electric and an ID.3, similar size vehicles, in my opinion. You look at the price difference. The ID.3 is quite a bit cheaper. It drives a lot further, so it's essentially a much better vehicle to drive, and that's just basically because they started essentially from scratch. Now, we also need to, the bottom end, looking at your complexity of your products, reusing components across multiple vehicles, and that's essentially a bit of a platform strategy, but also going beyond that definitely helps. But from our perspective, what is really focus areas is to integrate the development process, bring different disciplines closer together, and also front loading through simulation, actually using simulation to predict better. And we've been using simulation for a very long time, and we've talked about front loading for a very long time, saying, but this aspect is getting even more important nowadays, even though we've been talking about it for the last 25. So if we go to the next slide, you could say, okay, let's start with what people then call digital threads and these elements, essentially integrating the development process. That's a first instance, starting from your requirements, your product design, all the way to your design for manufacturing and so on. You integrate all that into a system, a PLM system, where people can really work together in an efficient way. That covers, in essence, the overall traditional product development as we see it. So you have very good views on what you're doing at every stage of the moment, and you can share data and so on. That's all fine. But if we then, in the next slide, go a little bit deeper and look at an electric drive system by itself, and think about a little bit what are the challenges here. We're going to have to build or to develop one box in which we combine an electric motor, a gearbox, and the power electronics. So we're now bringing together multiple disciplines from the design side, but also from the engineering side, because we're looking at mechanical issues, we're looking at electromagnetic issues, we're looking at definitely thermal issues that within these different systems all exist. So that's completely different from what we did with combustion engines, where an OEM would have an engine department, they would develop an engine with its control system. That's comparable to the electric motor here. And then they would have a transmission department, or they would go out to a supplier like ZF, Aisin, Borg-Warner, and others to buy a transmission bolted on there, and done. We have our driveline. Now we really need to collaborate here. And if we think about it, you have different disciplines, and I'm showing here power electronics. We're looking at the electroelectric motor, for which we will dive deeper in the rest of the presentation. You have your gearbox. All these elements need to come together. And in our concept that we work with is that all this collaborative engineering really needs to happen in parallel and collaboratively. So we're looking at this system, different components. We need to define what is that system and that system of systems, because the electric drive is part of a complete vehicle, but the electric drive by itself consists of multiple subsystems. So we need to define all those. We need to define the interfaces between them. We need to be able to cross-domain work across these interfaces, which means really a big challenge on how you integrate the program, how you make sure that everything works together at every stage of development. And we'll be looking at the conceptual stage first for like an electric motor, how to deal with the sizing. We'll look at things like the further development of that electric motor, but that happens in parallel also for all these other elements. And again, especially when we look at thermal aspects, for example, we have the power electronics that need cooling. We have an electric motor that needs cooling, or it will actually degrade rather quickly. And we have a gear system that needs cooling. How do we manage that? That's exactly what we try to achieve with our view on, with our ideas behind the Simcenter portfolio in terms of developing these systems. So if we continue, what are these challenges? And then just very quickly, 3 big blocks. We want to have an efficient motor, a very efficient motor that is essentially good, essentially we say we want to develop a good motor, highly efficient in a wide range of operating conditions, without any thermal effects, without any issues in terms of noise and vibration, perfectly integrated in the vehicle or integratable in the vehicle. But we want to do that at a reduced cost. We want to reduce the number of the amount of rare earth materials that we use in there. So the design of the motor is critical here to reduce those elements. At the same time, increasing the power density and minimizing the weight, but again, making sure that we don't get into any thermal issues there, and to accelerate that, to make that development faster, integrating, collaborating amongst the different disciplines, electronics, electrics, thermal, electromagnetics, and so on, is absolutely essential. Okay.
Thank you, Stephen. We're just going to take a break there and just launch a quick poll to get some interaction from folks. So we would be interested. You heard Stephen talking about the different challenges, but we've kind of summarized the poll a little bit into, you know, what's your main challenge? Getting a better motor design, effectively, you know, or a cheaper motor design, or getting that quicker to market. What's the challenges you're facing right at the moment with designing electric drives, motors, etc. So yeah, just letting that poll run. Also, as the poll's running, feel free to ask any questions in the chat as we go along. We will have time at the end for Q&A with both Stephen and Anthony. But if questions come to mind as we're going along, just post them into the chat or the questions box, and we will come back to them. So okay, looks like folks are voting. Yeah, I'll leave that open for a few more seconds, and okay, let's close that now. And I should be able to share the results with you. So if I click share, so hopefully on your screens you will see the results. So it looks like a majority of folks that voted are currently wanting just to improve motors, design better motors, and then we can see a mix of some folks obviously looking for cheaper motors and getting quicker to market. But yeah, it's a good mix there. So a wide range of challenges. So I'm gonna pass the ball back to yourself, Stephen.
Yeah, just for me to close off. And actually, the poll does help. I mean, it's not that I didn't expect the results. Absolutely not. I mean, that's what we are here for. We are engineers, so we want to essentially build better motors. That's key. And with the Simcenter portfolio, and it's a bit of thinking in terms of a bit of marketing here, but at the same time, think of it. I mean, when we want to have this collaborative way of working throughout the entire development process, the 4 pillars on which we build Simcenter and that are key in our thinking in how we drive that product forward, or that product family forward, is really being able to model the complexity, being able to, at each stage of the development, have the right fidelity models and trustworthy models available, such that you can take the right decisions in order to be able to go forward. At the same time, think of my comment on the different architectures that are possible or could be evaluated. We need to be able to explore possibilities. We don't want to stick with the very first design that came to our mind. We want to be able to explore and do parameter variations on things. And in order to do that, because that gives us more insight in what we are doing, we also need to go faster. And going faster means having fast solvers, like for example, when we talk about CFD calculation, being able to do that with GPUs and so on, or using reduced order models where we take a high fidelity model and compress it into something that is actually that runs much faster with a limited set of parameters available for changing. but also the process integration. The process, as you integrate the process better, as you make the link between the different tools that you need, when you make that link easier for the engineers, you increase that speed, and that allows you to really stay integrated. And that's what we say, staying integrated, being able to communicate between different teams in a consistent manner, connecting all the different activities that the people are doing. And with that, I would like to hand it over to Anthony, who is going to look at electric motor development and going essentially through a number of these elements, of these pillars that I just highlighted within the Simcenter portfolio, but then applying it to an electric motor development.
Thanks, Stephen. That's a really nice introduction to what I'm going to be doing. So we're going to talk a little bit about the motor design process. I expect most of you are at least familiar with the process of designing electric machines or other mechanical devices. And classically, we'd start by defining some operating requirements, either from data sheets and external sources or by doing internal system simulations and calculations. Using these requirements, we can develop an initial motor design, which will typically be either analytically based, so based on equivalent circuits, or based on existing data and fitting your requirements into that, or on simple analysis systems such as 2D, FEA, or other simulation techniques. When we look at the wider perspective that Stephen's just been talking about, where we want to be able to go deeper into the possibilities, we want to be able to look at all the little variables, we're going to start looking even deeper than that. We're going to start looking at advanced modeling, often in 3D purposes that go beyond the capabilities of our existing simulation tools. We'll even be looking at multiphysics tools, where we can take electromagnetic results and hand them off into CFD and thermal situations, or structural or acoustic simulations, and see how those react. Oftentimes, as with any system, virtual, you need to tie it to reality. And by being able to do further detailed design, we can more tightly link this to validation and verification that happens in the real world. Using this validation and verification information, we can feed that back in and make sure that our virtual designs correlate correctly to reality for when we develop them further. For today, we're really going to be looking at the middle stages here in the simulation process, how to initially set up a motor design, and how we might explore that into the detailed motor design when we move further along. Now, today's subject is really thinking with a lean towards thermals. Now, in electric motor design, there's a number of reasons why cooling can be a really important factor in your design process. When we run at different operating temperatures, especially high operating temperatures, we can see substantial negative effects to the performance of our machine. We might have high temperatures that could lead to reduced magnet strength. That'll lead to lower torque and lower power performance. We might see increased coil conductivity, leading to higher resistivity in the coils, higher losses, and more thermal buildup, creating a feedback loop. And in extreme conditions, both hot and cold, depending on your materials, we can see permanent damage. We can see permanent demagnetization in magnets, reducing the effectiveness of your machine for the rest of its productive lifetime, as well as damage to other materials such as liners and insulations in the coils, or the structural materials around the model itself. This can be highly detrimental and cause serious problems after devices have already reached market. Now, I believe, Adam, you have another poll question for our audience.
So I'm going to launch it now, and so this is really focusing in on this topic around cooling and how you handle that within your design process. So where in the design process do you typically, or where do you address thermal behavior in your designs. So in your requirements, initial 2D design, you might be doing 3D detailed work, or you might be doing some kind of testing or exploration of designs. So yeah, I can see some answers coming in. Whilst those are coming in as well, thank you for those who've already started posting some questions. Just a reminder, if you do have some questions, post them. We will get to them at the end. But I do appreciate that a few questions have already been shared. So, okay, Anthony, I've got some results coming in here. So I'm just going to give it a little longer, and then I'm going to close and share the results. And then it'd be nice if you would comment a little on this. So let me share those with everyone. So hopefully you can see on your screen. So the original question, where in the design process do you address thermal behavior? So quite a lot of folks are getting into detailed design there. 50% of the folks that responded have done that. I assume, Anthony, you can see those results. Any comments on those?
Yes. Yeah. So I guess these obviously aren't that surprising. Oftentimes you get skewed when you talk to designers about when they are thinking about thermals. They're either thinking about it right from the beginning in the requirements, or it's something that doesn't get addressed until much later in the design. And something that those of you who do only really look at thermal behavior as you get further in the design stages, I would encourage you to think about how you might be able to front load or move that process of addressing thermal behavior earlier in your design to avoid major problems or having to go back later in the design process. But that's part of what we're here to address today. So the next things we'll be looking at are quickly how we might use the Siemens Simcenter toolset to set up a basic electric machine model, and how we might use that basic model to start looking at behavior both on the electric and thermal sides. So we talked about the overall workflow for designing an electric motor earlier in that nice V-shaped slide. But now let's talk about the workflow a little more specifically, how a designer or an engineer might approach it. We have our initial specifications that have come from system simulation or data sheets being provided and requirements being provided by external sources. We can use this information to set our initial definition. We need to know initially things like power limits, limitations on our materials, or thermal considerations, if that's something that you want to take into account early. You might have ideas about the number of slots or poles, rough dimensions that you're interested in. Once we have that rough outline set up, we can start looking at specifics for the design. We can start looking at rotor and stator geometries, winding layouts and drive systems, and how we can size up our wires and specify our our machining process to design our pieces. Once we have a fully designed piece, we can go and analyze it. We can often use 2D analysis for rapid results that are accurate without having to be tweaked with adjustment factors. And this can give us basic information that designers might be interested in, things such as torque calculations, efficiency maps, and field saturations. But we can also start to use that information right from the beginning to look at thermal analysis and behaviors on that side of things. Once we're comfortable with how our machine is performing on an electromagnetic perspective, we can loop that into verification. Does this meet our requirements? Does this do what we expect it to do for our use case? And if not, we can loop back and start looking at it again, making modifications as we go. We can also take those results and pass them on to other solvers. We might be curious about the acoustics or the thermal and CFD sides of our design and how these tie into other physics. Using these results, again, we can come back, verify that we're meeting the requirements that were set out right at the beginning, and that the system is working as it should as an overall unit, not just the electric machine in isolation. We have a quick demo here where we'll show you very briefly the process in just a couple of minutes of a 2D design system from Siemens Simcenter. So this software is called Simcenter MotorSolve. It's a 2D initial machine design tool. We can see that we have cross-sectional area. We have on the left-hand side some areas of interest that we can select to view them. And on the right-hand side, we have some general settings that are available for us to define things like specifications, general dimensions, and importantly, we have templates. This is a template design-based tool, which makes it very easy to set up and adjust your model. We have several templates for rotors and for stators that allow you to choose your geometry. And we have access to import custom geometry using a DXF import functionality. Within these examples, we also can have the templates reverse and have an exterior rotor as opposed to an interior one. Inside the templates, we have access to all sorts of controls. We have access to settings about how we might skew or adjust overhangs in the rotor, but we also have dimensions that we can adjust, diameters, magnet sizes, and the like. Similarly, when we start looking at the stator adjustments, we have very similar controls there to help define the geometry of the stator, the size and shape of the slots and the teeth that we're going to be working with. In the stator windings, this is where we can set up information such as the control system for it, cross-section information about the slots, wire information, and the winding pattern layout itself. This can be automatically generated using internal algorithms in the tool, or it can be manually input should we want to define our own custom winding specification. In this view, we have lots of controls, including the ability to see multiple phases on multi-phase machines. Many large machines these days run 3-phase, and we have to make sure that the windings are laid out properly in all 3 phases. From the stator end winding page, we can set some basic information about the end windings. Often, this is just using these extra information to define extra resistance and parameters like that, and is not typically used in the electromagnetic simulations that will be seen in a moment. With our geometry set, we have to be able to define the materials, as they'll have a massive impact on the performance and behavior of our machine. We can choose materials for the rotor and stator, as well as the shaft and hub, to define our electromagnetic system from a large suite of materials that come with this software and are identical across the Simcenter suite to make sure that the same materials are available to you in any environment. Once we're happy with the electromagnetic design, we can start looking at some results from basic simulation. These can take the shape of standard performance metrics, such as torque speed curves that we might be interested in, as well as several other different metrics. You can see them all listed on the top left. We also have access to results more directly from the FEA analysis that happens, such as what we see there briefly. And we can check fields that resulted from this analysis. Time average fields might tell us about loss or demagnetization behavior. We might also want to look at the magnetic field at a particular instant in the drive cycle to make sure that materials aren't being saturated and that we aren't overrunning any material limitations that would cause problems and damage. With the electromagnetic performance under control, we can start looking at basic thermal settings where these losses are going to be transformed into temperatures. We can define rough geometry for a housing on a very basic scale, assign materials for the housing and other thermal parts of the machine, and then we can apply some basic cooling parameters. spray cooling, duct cooling, natural ventilation. This is not a CFD simulation. It is a very basic thermal FEA simulation using thermal transfer coefficients. It'll give us a good idea of how things perform, but it's not going to be as in-depth or as accurate as doing a full thermal CFD simulation further down the line in multiphysics tools. With all of these defined, we can look at information such as the losses that might be driving temperature buildup. We can look at temperatures based on a defined duty cycle. If you want to meet a certain standard, especially in electric vehicles, there's typically a duty cycle defined. We can look at a slice of the machine and see how those temperatures are distributed in a 3D slice to see what is going to be a concern, even with this basic cooling. Where are we getting heat buildup? Maybe where do we need to address it when we get to the further studies? Now, when we're talking about 2D motor design, there's a number of benefits using this as the first stage design. As we mentioned, template-based means that it can be very quick to automate the process. Somebody has already gone and done the work of parameterizing all these templates, and it's very easy to set up different templates, different shapes, different sizes, just from the control panel without having to manually adjust CAD models. Same goes for the winding design and the drive system. All of this has been pre-parameterized, and it's quick and easy to change if you want to test different variations. We have some preset experiments that we talked about, like the torque speed curve or the torque waveform that we saw earlier, as well as being able to see the 2D FEA solutions. As mentioned, this is a very early design tool, but we can still couple it to basic thermal analysis and give ourselves a first glimpse into how the machine will behave when we start to load it and when we start to heat it up. We can use this information to take into account how the material properties might change and how the machine behavior might change through the temperature ranges. Two of the key features here in tools like this is that we're able to export models back into 1D system simulations to ensure that our design, as it is designed, is behaving in the system as we expect it to behave. We can also look at the open architecture, which allows us to take the machine design that we've got and use that already defined parameter set and geometry and move it into more advanced simulation, whether that's 3D electromagnetic simulation or further multiphysics simulation around thermals or acoustics or other. One of the fun features of having such an open system and the many, many tools that are available to us through Simcenter is that we can link them all together without even noticing the connections. We can use our machine design to link back into our system simulation to see how the overall vehicle might perform with this machine design. We can hook up to a system optimization tool where it's taking parameters, it's optimizing based on system results, but it's modifying the machine. So we're doing optimization on the machine design to optimize the performance of the entire vehicle. Using this to make sure that we're finding a machine that doesn't just meet the paper specifications, but is actually meeting the entire requirements of our system as a whole without choosing anything in isolation. We can adjust all sorts of parameters, and really with the open connections, we can connect this and optimize based on any other physics that we're interested in as well. Often we get asked about how we validated our machines, our machine design tools. And this is just one example where a customer of ours wanted to validate the machines and went to test it against the BMW i3 machine. There's a fairly well-documented motor that's been tested in independent labs, and a lot of that data is available to the public. When our customer was using this tool to validate it, they built an identical model to the BMW i3 traction motor in the MotorSolve tool that we were just looking at. When they compared the results coming out of the 2D finite element analysis to the results that had been tested on a bench in independent laboratories, we found a very, very high correlation between the simulated results and the physical world results. This gives us huge confidence in being able to push this initial design system as a confident way of starting your design process. Now, we mentioned 3D design earlier, and it is an important part of the simulation tool, especially as we drive into higher performance and higher performance density machines, where every little bit of performance counts. 3D effects that we might not see in 2D simulations include end effects, fringing and leakage, for example, where you might have effects that are causing heat buildup, field leakage, or other performance degradation because of the edges of the model. We can also start to look at how we might address cooling in a 3D manner on our machine. We can change the templated designs to have impossible geometries that weren't possible in the template, and we can create non-symmetric cooling solutions that might be more efficient for our use case that we couldn't have modeled in 2 dimensions. You can hop on a slide, Adam.
Should be updated.
One case where 3D, one case where 3D modeling is exceptionally important is when we're looking at axial flux machines, and these are becoming more and more popular in a lot of use cases. Axial flux machines, by their nature, cannot be modeled in a 2D simplified way, and so we need to start with a 3D model. Through Simcenter, we have the ability to model this entire 3D geometry, and within a single environment, we can explore the electromagnetics behavior, but we can also take that model and those results and pass them into a structural solver or into a thermal and CFD solver to see how this machine will operate across a variety of different domains without having to leave a single software environment. This massively speeds up the development process and makes it a lot easier for communication between different teams and different parts of the development process. So as I said, we can have one single environment. Simcenter 3D is this environment from Siemens in the Simcenter ecosystem where we can build our design and we can initially look at the electromagnetics, but we can then take those electromagnetic results and we can look at the structural behavior and the acoustics that result from that. We might also look at the thermal behavior and the CFD analysis that'll help us manage that a little bit better. All of these can be tied together using design optimization tools where we can take the results from one simulation to modify the behavior in another physics domain, allowing us to make sure that we have the absolute best machine for our use case.